So section 5-2, I'm sorry, I messed up my outline here. But section 5-2 begins with meteorites and asteroids and then looks at the formation of the inner solar system planets. And section 5-3 describes the formation of the moon. And then sadly, this is the end of the astronomy section. So if you liked astronomy, this is a sad time. But if you didn't like astronomy, this will be a big improvement. So then we'll focus on the Hadean Eon and Archean Eon on the Earth, which was, I think, the first couple million years. And then after that, we'll look at some of the things that make the Earth habitable, such as our magnetic field and plate tectonics and our atmosphere. And we'll compare it to a few different atmospheres, Biosphere 2, which is in our area around Tucson, and then Venus and Mars. Then we'll look at the same old question, how special is the Earth this time, rather than how special is the solar system. Then we'll look at some philosophical and religious perspectives on Earth. Okay, so most of the data that tells us about the conditions in the early solar system is from asteroids and meteorites. We can't look at the Earth because everything's been cycled down into the magma and everything's been lost as far as data on the early Earth. So scientists can collect and evaluate meteorites when they impact the Earth. But what if you could evaluate an asteroid? Well, recently, the University of Arizona sent the OSIRIS-REx mission to the asteroid Bennu. And you can see the leg of OSIRIS-REx landing on Bennu in this picture on the lower right. And just think, somebody from the University of Arizona made all the calculations for that leg to touch down there. Just imagine how much had to go into that and how it had to work the first time. I mean, they only had one chance to land on that asteroid. And then this is the asteroid they landed on. It's a lot more rocky than they thought. They thought it was smoother, but they were able to take pictures of it while they had their little orbiter there. And after all that effort, all they collected is 120 grams of material, which is like the weight of a small apple. I just can't imagine they could only collect that much material as a sort of a soil scientist guy, So I'm thinking they should have had a soil scientist work on their soil collection efforts. Anyway, scientists classified Bennu as a carbonaceous asteroid from the Apollo group, which means it orbits in the green range here. So here's Earth. And so this green range is where the Apollo group asteroids are orbiting. And there's 18,874 Apollo asteroids, of which Bennu poses the greatest risk. So it has the greatest risk of causing a catastrophe on Earth. And that's because of its possibility of impacting the Earth, not now, but in 100 years. But also because it's a rather large asteroid. It's 500 meters in diameter. But in comparison, the Chicxulub asteroid that caused the dinosaur extinction 65 million years ago basically would have wiped out all human life because it destroyed the climate for 10 years, sent us into a global winter. It was 10 miles in diameter. So it's a lot smaller than the Chicxulub asteroid, probably like 50 times smaller when you talk about mass. Okay, well, this is not germane to the chapter, but just in case you're interested, astronomers plotted the paths of the Earth, Osiris, Rex, and Bennu. So you can see Bennu here is in the green and Earth is in the blue. So you can see why it could possibly impact Earth, or why it would be a desirable asteroid for us to send a mission to, because it's relatively close to the Earth. And then this is just the path that the OSIRIS-REx took as it landed on Bennu and then left Bennu and came back to the Earth. I actually knew a mechanical engineer who was working there. I never asked him what he did. Probably couldn't tell me. No, it's not secret, I guess. But anyway, there was a lot of effort put into making this thing work. It was really amazing. So this is a picture of the asteroid belt between Mars and Venus. So here's Mars and Venus, Mars and Jupiter. Here's Mars, here's Jupiter. And although it's populated by 300,000 to 1 million asteroids and dust, meteoroids and dust particles also, the total mass of objects in the asteroid belt is far less than 1% the mass of the Earth. I think it's 4% the mass of the moon. So it's a lot of asteroids, but they're very small. And the reason they're so small is Jupiter caused the orbits of the asteroids to be unstable, and they never could accumulate into a larger planetesimal. There is one, I can't remember what they call it, a protoplanet or something, Ceres, which orbits on the inside of the asteroid belt. So that makes sense, since Jupiter is destroying the orbits of the asteroids. The biggest planet in there, Ceres, accumulated on the inside of the asteroid belt. Or they call it a dwarf planet. So this is the most analyzed meteorite to strike the Earth. It's the Allende meteorite. And meteorite hunters, and there's some very interesting videos on YouTube about meteorite hunters. You know, they go out and find meteorites. I don't know if you've seen them, Claire. Yeah, they're pretty interesting. Interesting people. But they can actually make money off of the asteroids because they can sell them to scientists. But anyway, meteorite hunters found 2 tons of this Allende meteorite. And you can see that they've named this Pueblito Allende and Valle de Allende, if that's how you say it, Allende. But anyway, they found 2 tons of this meteorite scattered across a strewn field in Chihuahua, Mexico, between, I'm saying all these names horribly, I'm sure, Jimenez and Parral. Okay, so this Allende meteorite, which I'm showing a section of here, has calcium aluminum rich inclusions, which are the white particles in the meteorite. And the abbreviation for these particles is CAIs. And so they're mineral crystals that contain metals such as aluminum and titanium, as well as alkaline earth metals such as calcium and magnesium. And they range in size from submillimeter to centimeter diameter. And scientists use these particles to date the age of the universe because they're the, or not the universe, the solar system, because they're the oldest particles that we know of in the solar system. Okay, and then another thing that's found in meteorites are chondrules. And scientists know that chondrules formed in the solar system in flash heating events in which the small particles were heated and then melted and then rapidly cooled and formed spheres. So the meteorites that contain chondrules, and actually because most meteorites contain chondrules, they're all called chondrites. So the meteorites that contain chondrules are called chondrite meteorites. And scientists do not agree on how the chondrules formed, and they don't even agree on whether they formed within the nebula, you know, within the protoplanetary disk, the cloud, or within planets or planetesimals. So there's not a lot of understanding of how they formed. They just know they formed by heating and cooling. One interesting thing is the chondrule chronometers, which are the radiometric dating analyses of chondrules. They indicate that they formed over a few million years, possibly between 300,000 years after the solar system formed and 2.5 million years after the solar system formed. And the way they know the ages that things solidified, is that's how radiometric dating works. Is it, as it doesn't just assume, but it's all parent material at the time the rock hardened, such as magma from a volcano. And then they can track the development of daughter products over time, and that tells them when the solidification occurred. So based on that type of analysis, they know that the chondrites formed between 300,000 and maybe 3 million years after the formation of the solar system. There were flash heating events in the early solar system in the T Tauri phase, and that lasted possibly from 100,000 to 1 to 3 million years after the formation of the solar system, which kind of goes along with the dates of the formation of the chondrules. But even the T Tauri phase, there's different estimates by different people. So even that's a little bit uncertain. Yes?
Is that big or is that small in like real life?
I forget how big this is. I think it's pretty small. I copied it quickly off the internet because it was the coolest looking one. But it might be, it's somewhere probably between the size of my thumb and the size of my hand, something like that. Well, so these are, the chondrules are olivine. A lot of them are, let's see what it is. Yeah, so they're formed from, obviously they're different colors, so they're formed from slightly different minerals. But I don't know if there's, maybe somebody could look it up on the internet, look up chondrule jewelry. But they certainly are cool. I mean, you could see why a meteorite hunter could sell this for a lot of money. This is a really cool looking thing. Most of them don't look this cool, but well, the chondrules are different elements, and the way they formed, and also the CAIs, is that there was a process called condensation, where as the solar system cooled, the metals and some of the rare earth metals combined and formed minerals. And then they solidified as it cooled even more. So that's how they know, like, the CAIs formed at the beginning of the solar system, because that was the time at which the solar nebula cooled. And then these metals in the gases and other rare earth metals form minerals, and those form these particles, those CAR particles. And then those CAI particles, I guess, were modified by these flash heating events, which caused them to be spheres. Did you find some jewelry? Oh, cool. Is it just one thing, or is it like the whole thing?
It looks like a lot of it, like they just they wrap it in like, so they don't have to actually drill into it or like.
Oh, okay. So they just hang like a piece of it.
Yeah, like it looks like it's just like either they like shape it, like it looks like they can't like.
Yeah, it doesn't look very malleable, really.
Yeah.
But I would wear one. I mean, I don't wear necklaces, but I could see wearing a chondrule necklace.
You have a story to tell.
Huh?
Then you have a story to tell everyone. And they're like, oh, what's that?
Yeah, I mean, I'm the first person who needs a story to talk about when I meet people, because I just don't come up with stories on my own. Right. A good idea. Or even better, you could make one for your dog. And then you'd have your dog to talk about and the dog necklace to talk about. Okay, well, so with all the meteorites that have hit the Earth, scientists have been able to, I don't know how many there's been, but they find that they all classify in two groups. There's non-carbonaceous meteorites and carbonaceous meteorites, or non-carbonaceous chondrites and carbonaceous chondrites. And so they do these chemical comparisons. And so this is like plotting the amount of something titanium to something chromium or something like that. And so you can see that all of the non-carbonaceous chondrites grouped together, as well as the Earth and Moon and Mars, and all of the carbonaceous chondrites grouped together, along with Bennu. Bennu is a carbonaceous asteroid. And so they know that the non-carbonaceous chondrite meteorites formed in the inner solar system and the carbonaceous chondrite meteorites formed in the outer solar system. So the non-carbonaceous meteorites, as well as the Earth and Moon, have low fractions of water and low fractions of volatile carbon molecules. And the carbonaceous chondrites have 5 fractions of water and high fractions of volatile carbon molecules. For example, Bennu asteroid, which is a carbonaceous asteroid, has 10% water by weight. So they brought that sample back, and one of the first things they did was they analyzed it for the amount of water. That's like one of the primary things they wanted to know. I just watched a YouTube video where they were so happy about this. The NASA person was like just almost ready to jump out of his pants. He was so excited. And they noticed that they also had 5% carbon organic molecules, which is a high amount of carbon. These were contained in hydrated clay minerals. So just like in soil, clay minerals hold water. On the asteroid, the clay minerals hold water. Clay minerals are like plates, and they're just connected together, and water goes in between them. Also, Bennu, due to its high fraction of voids, 40%, like caves and pores, might also hold water and organic molecules in those voids. They don't really know from the soil sample. Okay. In contrast, Earth, which formed from non-carbonaceous planetismals, only has 0.02% water by mass. So we have an extremely low fraction of water on Earth. 1/50% of water on Earth. And only 0.3% of the Earth's water is on the surface of the Earth. So assuming that the fractions of water on Earth are suitable for intelligent life, the high fractions of water and organic molecules, such as in Bennu and the carbonaceous meteorites, or in the outer gas or water giant planets, would be unsuitable for a planet that supports intelligent life, because there'd be no continents. The whole surface of the Earth would be covered by water. So the Earth would be covered by oceans if it was formed from carbonaceous planetismals. Or if it didn't have a geologic system that only allowed 0.3% of the total water on Earth to reach the surface. Okay, so with that data on the separation of the carbonaceous and non-carbonaceous asteroids, scientists tried to determine what factors separated the inner and outer solar system. And one proposal, I think it started about 20 years ago, is the Grand Tack hypothesis, which is that Jupiter and its friend Saturn formed early in the solar system. So you can see here within 70,000 years. And they migrated into the inner solar system, throwing all of the asteroids out of the gap. So here's Jupiter and its friend Saturn migrating into the inner solar system. And then you can see that everything behind them is depleted. And then about after 300,000 years, they decided they'd had enough of the inner solar system, and they migrated back to their original positions, leaving behind a few carbonaceous asteroids. And the reason that they do that is that the outer part of the asteroid belt is carbonaceous asteroids. The inner part is non-carbonaceous asteroids, not completely, but mostly. So whenever they make these kind of models, they have to make the results agree with what they observe in the solar system. So they know that the inner solar system is primarily non-carbonaceous asteroids that are completely different from the carbonaceous asteroids. But there are a few carbonaceous asteroids in the inner solar system, so they have to account for that. Now, Bennu, it formed in the asteroid belt. So a lot of these smaller objects like Bennu, they came from planetesimals or objects that were maybe 100 kilometers in diameter. And the asteroid belt is kind of a crazy place where, you know, there's 300,000 things orbiting around, crashing into each other. So any planetesimal that might have been there might have crashed into another and then broke apart. And then that's what forms all these meteorites, or meteoroids when they're in space, meteorites when they hit the Earth. So that's the explanation for these meteorites, is that they were once part of large planetesimals, but then those planetesimals broke up, and that's why there's meteorites in the solar system. Okay. So that was the grand tax scenario. But the grand tax scenario where Jupiter and Saturn migrated in, it's not as popular these days with planetary scientists because it requires extreme fine tuning for those planets to start migrating into the inner solar system and then migrate out. And scientists don't like fine tuning. So they're trying to find other answers. So Morbidelli is one of the guys who conceived of the grand tax scenario. He's on this paper too, which may or may not be significant. But what they're proposing here is that Jupiter formed, so there was these planetesimals forming in the inner and outer solar system, a little bit of mixing, but then Jupiter formed and blocked the mixing between the inner and outer solar system. But then Jupiter threw a few of these outer solar system carbonaceous chondrite asteroids or meteorites into the inner solar system just by gravitational like deflection. So that accounts for that. The fact that there's carbonaceous chondrite meteorites and carbonaceous asteroids such as Bennu in the asteroid belt. Okay, so that's one scenario. And then you can see that they're thinking that the inner solar system was hot. And so that's what explains the fact that there's non-carbonaceous asteroids. The water's been depleted, whether that's like a transition disk or a dust disk or it'd be probably not a protoplanetary disk if the water in the asteroids is depleted. This was in 2020, this paper. Okay. So this figure shows the composition of the planets, and notice that the outer layers of Jupiter and Saturn are hydrogen, metal, and gas, while the outer layers of Uranus and Neptune are water, which makes sense since they formed in the coolest part of the solar system where water ice would not have been volatilized. However, scientists think that the cores of Jupiter and Saturn contain water, just like Bennu. So even though it's a rock core, they think that there's also, you can see here, rock and ice. So there's still water in these cores, but in the inner terrestrial planets, there's hardly any water. Remember, it's, I think, 0.02% water on our planet. Oops. Okay, so this is that picture again of H.L. Tauri. So this is a ALMA observation. Remember, that's that telescope array. So this is a 100,000-year-old planetary system or disk. And so, like I said before, I don't know if I said, but they're all excited that they found water in the inner disk where planets are forming. So they're starting to accumulate evidence that there was water in the inner solar system when the inner planets formed. And the reason for that is that Lichtenberg explained in 2021, I think he was the first one, why the inner planets formed in a wet part of the disk but are dry. So, so he proposed that the inner planets formed in the protoplanetary disk. And so I'm showing the disk reaching to here. And this is what's called the snow line. So it's cold here, warm here. And the idea is that pebbles, so pebbles are like small 1 centimeter rocks that migrate inward. The idea is that they'd build up here and these pebbles would have water, water, ice, and dust. And then inside of here, there would be condensation and sublimation of silicates, water, and carbon dioxide. I also got this from Grewal, another paper that I'm going to show you in a minute. But then this would cause a high density of these pebbles. And they think that this is what caused maybe that part of the disk to collapse and form planetesimals. So if there's enough gravitational force due to high density of pebbles, they might all just collapse at once and form planetesimals very quickly, like within the first 100,000 years of the solar system. Also, another reason to believe that the protoplanetary disk was inside of the Earth at the time the Earth formed is that models, they do computer models of the protoplanetary disk and the movement of all sorts of things, planets, dust, and whatever, into the inner disk. And what was I going to say? Well, they do models, and they can calculate how much density there is in the inner disk and what it would take for the disk to collapse and so on. And so that's called gravitational collapse, I think. Okay. So what was the secret to the formation of the dry inner planets? It was aluminum-26 radiation, which is extremely high energy radiation, gives off a lot of heat. And the half-life of aluminum-26 is 700,000 years. And the supernova that exploded that caused the collapse of the cloud and formation of the sun, it would have produced aluminum-26. And so if the inner planets incorporated aluminum-26 while it was still in a very active phase of radiation, less than 700,000 years after the supernova explosion, then that would have heated up the planets and all the water and carbon materials would have volatilized. Not all, but most would have volatilized and left the planet. And so there's been papers on how much energy would be released by aluminum-26. And they figured out that it's high enough energy to heat up the planetesimals. It wouldn't heat up like meteorite sizes because there'd be enough surface area versus volume to allow radiation to escape the meteorite. But for a planetesimal, which is maybe 100 kilometers in diameter, there'd be a huge amount of energy inside, and that would heat up the entire planetesimal and cause the water to gas out into space, water and volatile organic carbons. Also, iron-60. Remember we talked about that, I think, with respect to the being produced by the supernova. And so that's how they know that a supernova exploded near the Earth or the solar system when it formed. But anyway, aluminum-26, this is a logarithmic scale. Aluminum-26 has about 10 times more heating value than the iron-60. So that's probably, this is not for sure. This paper just came out in 2024. This is cutting edge research where they're proposing a change. There was like 1,000 papers on Jupiter causing the formation of the inner solar system. And so this is going to be controversial, but I think, I first noticed this back in 2021 when this first paper came out. I noticed it right away. But then I was curious because I went back and looked at it while I was preparing for this lecture. And there's a lot more papers coming out now. So what it tells you is this is gaining momentum, this idea. So it'll be very interesting to see what happens in the upcoming years. Okay. So another paper that came out was this paper by Grewal. And he looked at iron meteorites. So here's a famous iron meteorite in Namibia, the Hoba meteorite. I think it's the largest meteorite in the world. So they built this little observation place to look at it. But he evaluated the scenario of the inner solar system planets forming beyond the water snow line. And he looked at the chemistry of these meteorites, which would have been in the interior of these planetesimals, because iron would have sunk to the center. And so, so this is another type of meteorite. And so he said that there's two possible formation scenarios for the NC asteroids and meteorites. One is that they formed outside the snow line in a water-rich portion. And that the other is that they formed at what he called the silicate condensation line, or more like the dust disk. And so he used the iron meteorites to evaluate these two scenarios. So he observed that the non-carbonaceous IMPBs, and I don't know how he did it, but he's like a chemist. They formed 2 million years prior to the carbonaceous IMPBs, or iron meteorite parent bodies. So the meteorites that are made of iron. And so that means that the inner solar system IMPBs were earlier than the outer solar system IMPBs, not vice versa. And he said that there would be two possible explanations for his observations. One is that the non-carbonaceous planetesimals formed without water, or that there was 2 million years separation in time. And he said the only explanation is there's 2 million years separation in time, because the inner planetesimals formed from initially carbonaceous materials, and then they became non-carbonaceous. Okay, so he looked at the oxidation levels of non-carbonaceous and carbonaceous materials. So here's the carbonaceous materials in blue and the non-carbonaceous in red. And he said they all had the same oxidation, which indicated to him that they all formed in a wet protoplanetary disk. Okay, so it looks like we're moving in the direction of the interplanetesimals formed wet and then dried out. Okay, so let's move on to the other sections. I'll have to go very quickly. But actually it's section 5-3 is the formation of the moon. And so that chapter, we have some nice videos there that you can look at. There's some new ideas, like as the whole Earth and moon became a disk sort of thing. Then we'll look at the Hadean and Archean eons, and we'll look at some of the evidence for the earliest life. Earliest life formed like 3.8 billion years ago. There's actually even some evidence that there was life in the Hadean eon, possible evidence. This is a banded iron formation, which indicates surges in oxygen due to algae. Algae had blooms and then increased the oxygen level, and then it was reduced after that, and then there was another bloom and so on. So they use rocks like this to analyze early life and so on. Okay, then we'll look at plate tectonics, where we have, it's very important for our planet to have plate tectonics, to have the atmosphere that we have due to volcanoes and so on. So we'll look at the cause of plate tectonics on the Earth. It's also very important for us to have a magnetic field to protect us from high energy solar radiation. So we'll look at the causes of the Earth's magnetic field. Also talk about some other planets with magnetic fields like Jupiter. Then we'll look at Earth's atmosphere and we will compare it to Venus, Mars, and Biosphere 2. And we'll talk about just what makes our atmosphere so habitable, you know? Why are we able to survive on Earth so well? Then we'll look at a couple scientists who, and neither one is, I don't think, religious or anything, but they're talking about the frequency of life in the solar system or in the universe. And we'll look at a reevaluation of the Drake equation. So how common is the Earth? Is it rare or is it special, if you want to call it that? So again, we have the same philosophical and religious perspectives, mediocre Earth versus rare Earth, atheist, theistic evolutionist, progressive creationist, young Earth creationist. So even the characteristics of the Earth in the solar system are probably rarer than we might have thought with the magnetic field, plate tectonics, atmosphere, and so on. And then just revisiting Arnold Guyot briefly. So he thought that the third day was the formation of the Earth in the disk of the solar system. And until recently, I don't know if I thought it was very well supported. Well, I did think it was supported, I have to be honest. But there was this difficulty that the Earth formed dry because the third day says, then God said, let the waters below the heavens be gathered into one place and let dry land appear. Well, if the Earth formed from water, wet part of the disk, and then dried out, this would be a pretty good summary of that process. So yeah, I think that things are improving as far as Arnold Guyot goes. All right. Any other questions? Great. We'll see you next time.